Alright friends, welcome back. In this video I'd like to cover the next section of Chapter 2 in your textbook, and that's going to be Section 2.4. And in this video, the title of this section is called A Library of Functions. And so what I'd like to do in this video is talk about what that means, and then take a look at a couple of examples where we are taking a look at what that means and using it to solve problems. So basically what a library of functions means is basically we're going to be doing just that. We're going to be constructing ourselves a library, or at least a systematic way of being able to think about how we can take some of these more basic graphs right here and then change the function formula and then observe how that might change what the new graph might look like, okay? And we do characterize that by kind of using this analogy of a family with a parent and a bunch of children, right? So these are all the different families of functions that we're going to be taking a look at here. So there's 8 total families, right? And in this video specifically, we're going to be taking a look at your linears, your square roots, and your quadratics, although all these other different types of functions and relationships we've talked about throughout the year, they will have basic shapes to their graphs as well here. So let's just run through those real quick. So we first have our constant functions, and of course these are the functions whose function formula look like y is equal to just some number, right? So these would correspond to what you might have referred to as a HOI in a previous algebra course, okay? So y equals a number. You guys know that those always correspond to horizontal lines. Your linear family of functions. So again, when we talk about the parent function, we're talking about the most basic example of a function of this type. And so y equals x would be the most basic function. You know that all the members of this family look like y is equal to mx plus b. And again, the most basic example of that would be an example where playing the role of your m, your slope, that's going to be the number 1, and playing the role of your y-intercept is going to be 0. Okay, and so we consider that to be the parent. And then again, the idea with a parent function is that if you were to change that 1 and that 0 to another number, you would get different variations on your linear functions, and you would get different variations on what the graph would look like, okay? So that's why we call these the parents, because these are the most basic ones. If we change the function formulas of the most basic ones, we're going to get variations of those graphs, which we do call children functions in some contexts. So I know that kind of seems a little bit silly, but that's actually what we call them. All right. Here are the next 2 families. You got your square root family and your absolute value family. So you can see the parent functions there. Again, these are the most simple examples of functions of these types. Just straight up y is equal to square root of x, y is equal to the absolute value of x. Again, we could start changing these function formulas. I could maybe like put a 2 out front, or maybe I could just go ahead and add a 3 out back. Again, this would give us different variations of these functions, and the graphs would look a little bit different if we started to do that. So moving right along here, we have our cubic family of functions, and so that has a pretty interesting shape there. Again, if we were to start to change that formula, we would get different variations on that shape. Moving right along, your quadratics. Again, we're no stranger to our quadratics after having gone through Algebra 2 in the earlier part of this course. One of the ones that we may be new to here is what you call your greatest integer function, okay? And so the graph of this actually is pretty interesting, because what you might find is that people typically call these sorts of functions step functions, because if you were to look at their graph, they basically just have these same iterations of their piece going infinitely in more of like a stair pattern, okay? And so that's why people typically refer to these as step functions, because the graph kind of looks like steps. But this would be the parent function of that, just the greatest integer of x, and we'll talk later in the video about specifically what that means. And then, of course, we have our reciprocal family of functions. And so we learned that this shape is called a hyperbola. And we did a little bit of work with your reciprocal functions recently, so hopefully that's still fresh in your mind, right? So these are the basic families that we're going to discuss. What I'd like to do for the rest of the video is specifically take a look at a couple of examples involving certain families that you see here. So let's take a look at that, right? You notice that example number 1 is one that I already did out for you, all ready to go. Again, just to save some time in the video. And again, because we've talked about these topics fairly recently, I feel pretty comfortable just kind of blazing through this one. But you notice what they gave you, right? They gave you f of -3 is equal to -8, and then they gave you f of 1 is equal to 2. Now, what I don't want you to forget is that this is function notation to stand for the fact that your input was -3. So remember that your input is typically what we call x, and your output is going to be -8 here. in this notation, and that is typically what we refer to as y. So later when we get to graphing these, we have the y-axis and the x-axis. We can go ahead and model that relationship between input and output by graphing this function, and then we get a better feel for how x and y are related, right? So just don't forget that we could translate from the function language to the language of ordered pairs, something that we might be able to plot in the xy plane pretty easily. And then the work for everything is right here, right? So I'm basically just using some of the previous formulas that we've reviewed, ones that you first learned in previous algebra courses here. I'm just finding the slope of your linear function. We were told that it was linear after all in the directions. I'm just finding the slope using the slope formula. I got that as 5/2. And then after that, I'm picking one of my points, and I'm using my new slope, and I'm using my point slope formula to get the entire equation of the line. I chose to go ahead and go with the point 1, 2 as opposed to -3, -8 because, again, just make your life easy. You don't have to deal with those negatives if you can avoid it, right? So, again, you get a final answer there of y is equal to 5/2x minus 1/2. And then if you were to go ahead and graph that, you can see that that's done right there. Pretty simple. Let's go ahead and get a better feel for this greatest integer function here, right? So again, this might be a new symbol for you, this double bar bracket symbol, but what this means is simply what it states right here. It says this symbol means the greatest integer less than or equal to the number inside, okay? And so this is the trick to figuring out what the outputs are going to be depending on what the inputs are in between the brackets. So you're going to think about the greatest or the largest integer, which let's remind ourselves what an integer is, right? So basically your integers are your counting numbers. You've got 0 in that list as well, and you also have your negative counting numbers, right? So that list would look like -2, -1, 0, 1, 2, and these lists keep going in both directions towards negative and positive infinity. So if it's not a number that shows up in that list, it's not an integer. So when you're thinking about this, you're thinking of the greatest number in this list that's less than or equal to the number inside the bars, right? So let's take care of a couple of examples as far as that's concerned. So the greatest integer of 1. Well, 1 is already itself an integer, right? So it shows up in that list of counting numbers and negative counting numbers. So the answer to this would just simply be the number 1 itself. 1 is the one that is less than or equal to 1 there, right? So we next have 1.3, right? So 1.3, the greatest integer that is less than 1.3 would actually be the number 1 itself, okay? And you're going to notice that that's a pattern here, right? As I move on to the next one, I have 1.7. I know that that number, if you were to round it, you would round up to 2 because the 7 there is, greater than 5 and so on and so forth. But again, this function is defined to be the greatest integer less than or equal to the number inside, right? So the greatest integer less than this one would, of course, be the number 1 again. And you might guess what the next answer is going to be, right? Even though I have 1.99999, whatever, again, something that's super close to 2, I want the greatest integer that is less than this number, and that, again, is going to be the number 1, okay? Just don't forget that in this context, when you think about less than, right, we could think about that in terms of the value and just kind of think about it that way, but remember, in terms of the number line, we mean to the left of. So to the left of on the number line, right? And that makes sense, right? Because if you have, one of our previous examples, let's go ahead and take this example right here, 1.7. If we were on the number line, maybe say 0 is right here, 1 is right here, and 2 is right here, we might graph a number like 1.7 to be approximately about right there. We're asking what is the integer, the greatest integer that is less than 1.7, and even though we're super close to 2, we're going to go to the left of 1.7 and say that that result would actually be the number 1. That's the greatest integer of 1.7, right? And so when we deal to negative territory, that interpretation is going to be very important to keep in mind, because if you have the greatest integer of -1, well, we have less than or equal to, right? And -1 is itself an integer, so that result is pretty easy. We'll just say -1 there. But if you move on to the next one, right? So -1.3. Remember, in terms of the number line, if you were to go ahead and draw that, right? Maybe say here's 0, here's -1, here's -2. -1.3 might be something that you graph approximately right here. Again, if we stick with that interpretation, we might say, even though that it's super close to -1, again, the interpretation is less than or equal to, or in other words, to the left of on the number line. So the result there, weirdly enough, would actually be -2. So it says here that, recall, -1 is not less than -1.3 because it's not to the left of -1.3. It's to the right of -1.3. So I know that this is going to take some getting used to. It's a new type of function, but that is exactly the way that it's defined. You just want to kind of think about what the greatest integer is, or the greatest counting number, positive or negative, that is less than or equal to the value inside of those brackets. So one of the examples that you'll run into on your homework is going to be this idea of a piecewise defined function, okay? And so piecewise means, of course, in terms of the machine, that we've talked about these in the past, right? Your machine is going to take a look at your input first and then put it into one of two categories, and then it's going to give you the output depending on the description attached to that, that category, right? So you notice that I've colored my two categories here. I have my blue one and I have my pink one, right? And so my first category is going to be the one that my machine is going to go with if what I give it is less than or equal to 1, and then the pink one is going to be what my machine goes with if I give it something that is greater than 1. And so you notice that I've already kind of gotten us started here by coloring my two regions, and I put this big dashed line right here at my cutoff value. Because my two categories kind of split apart at that value of 1, I went ahead and drew a dashed line on my grid in that way, and then everything that's left of +1, that would be all the ones that are less than 1. I've colored that blue to kind of stick with the same coloring convention as what I did up there in my piecewise function. And then, of course, all the ones that are greater than 1, I did those in pink. All right. Now, in order to graph these functions, we need to be very, very careful because, again, that cutoff line, that dashed line right there, that kind of cuts off my two categories. And so I can only graph so much of these machines up to the place where I cut off, okay? And so to give us an easier time with that, I've got some tables drawn here. We're going to kind of think about plugging in some values. And so let's go ahead and start with that blue one right there, right? So that's going to say if the input that you give this machine is something that is less than or equal to +1, then the machine is going to do this with it, right? It's going to double that input and then add 3 to it, okay? So let's just think about a couple of the values that are close to my cutoff, right? So because I can be or equal to 1 here, that means that I can actually live on top of the dashed line in my blue category here, right? So if I were to plug in 1, then what would I get? Okay, well, 2 times 1 is 2. If I were to add 3 to that, I, of course, get 5. Okay, so that'll be the first point that I plot here, 1, and then go up 5. I'm going to put a solid dot there because I can be equal to 1 here and still have an output. So on my boundary line there, I can be equal to 1, so I'm going to put a solid dot. And now what I want to do is I just want to go ahead and pick some other input values that live in that region and plug them in and get the corresponding outputs. So 0, how about, let's try that. So 2 times 0 is 0, plus 3 is 3. We could do -1 and -2. If we were to take 2 times -1, that'd be -2. Add 3, that'd be +1. If you were to take -2, plug it into my blue category up there, 2 times -2, that would be -4 plus 3, that gives you -1. This just gives you a bunch of different points that you can plot, and you'll notice that when you do that, you are going to get this linear-looking skeleton of functions. And this gives us the ability to go ahead and line up a straight edge to this and go ahead and draw a complete picture of what that line might look like. Now, you notice that I'm not going to go ahead and draw the part of this graph inside of my pink territory because that is an entirely different category. Okay, I'm only going to draw enough of that line up to the place where I reach my cutoff value. Okay, and now what we might do is go ahead and move on to our pink region. Okay, so this is where the function is going to start to split off. If we now give it inputs that are greater than 1, then we're going to graph an entirely new piece of this function. Okay, and so let's go ahead and do that, right? So we cannot be equal to +1 on this pink piece, but let's just go ahead and figure out what that value would be because that's going to have to be something that we mark on the graph regardless, right? So if you were to go ahead and make that input negative and then add 4, which is what your pink region does, right, then what you would end up with there is +3, right, because -1 plus 4 would give you a +3. So that gives us a point that we can plot. Now, we're not going to do this with a solid dot because that would imply that this is actually something that belongs on our graph, and I cannot equal 1 on my pink region. So when I go ahead and do this, I am going to go ahead and put a marker at 1, 3, but I'm going to go ahead and leave a little bit of an open dot there just to kind of signify that that is a marker that I wanted to call your attention to, but it's not filled in because that's not in my pink category. 1 is not in my pink category. Okay, let's just go ahead and do some other inputs. Now, again, we're looking to the right side of +1, so I'm going to pick some other ones here, like maybe 2 and 3 and 4. That'll give us a nice idea of what this is. Again, this pink category, it makes your input negative, and then it adds adds 4. So if I take negative 2 plus 4, I get positive 2. Negative 3 plus 4, I get positive 1. And then negative 4 plus 4, I get 0. Okay? And you could do more, but we're just trying to get a feel for what this looks like. So if I just go ahead and plot those points here, you'll notice that my shape is going to start to look a little bit like this. And I can now go ahead and take my straight edge here and line it up. And again, I'm only going to draw the portion of this machine that exists in my pink region. I'm not going to go ahead and dip over there into my blue region because that has a different function formula attached to it. And you might get an appreciation now for why this is called piecewise, because if I go ahead and get rid of my coloring here, then you'll notice that I do end up with 2 separate pieces of this function that are disjoint. They don't connect to each other. They kind of break apart at that boundary line of x is equal to 1. So I definitely think that using the color helps here, but when you see this in textbooks and in other online resources, they may not be so colorful in their interpretation, but that would be the exact same type of thinking that you would want to go through to graph one by hand like that. Moving right along here in the video, what I want to do is I just want to kind of study the wider sense of being able to change one of your parent function formulas and how that might affect the graph, right? So you've seen this in a previous algebra course, so we're just going to go ahead and blaze through these, right? If you start off with an original function, say y is equal to some function of x, and then you start changing the function formula in the following ways. Maybe you go inside to the input and you add c, or maybe you subtract c, right? So again, that's going inside to the input and adding or subtracting a number. What does that do to the graph? Well, in our interpretation of it, we're going to say that that's going to move it that many units in a certain direction. And because we're doing it to the input, it's going to be on our input axis, or in other words, our horizontal axis. So this is going to move us to the left or to the right. If you see plus c, that's going to move you to the left. If you see minus c on your input, that's going to move you to the right. And I think OneNote is about to crash on me. There it goes. Wonderful. All right, let's get that back open. Good old Microsoft. Okay, there we go. All right, so again, I know that it seems a little bit weird to see a plus c and then interpret that as moving to the left, and then to see minus c and interpret that as moving to the right, because typically that's kind of like the backwards directions. But the interpretation here is that when you see x plus c, the interpretation goes that you are taking x minus a negative number, and it's that negative number that moves us in the negative direction, which is to the left. Okay, if you see x minus c, that's going to be interpreted as x minus a positive number c. And so it's going to be that positive number c that moves us in the positive direction horizontally, which is to the right. Okay, now let's say instead that you were to go ahead and instead of adding or subtracting a number to the input, you go outside and start adding or subtracting that number to the output, f of x. Well, that's going to move you in the output sense, or in other words, the vertical sense, the y-axis, okay? So in that interpretation, we're going to go ahead and say here that these follow the usual conventions, right? So if you see plus c, that's going to go ahead and move you up that number of units, c, and if you see minus c, that's going to move you that number of units down. Okay, and so really the only kind of weird sense you guys are going to have to make sure that you remember is when you start adding or subtracting numbers to the input. And the reason for that is because there's operations occurring to the input, and so if we go ahead and introduce that other one, like adding or subtracting a c, that's going to move us in these directions respectively. Okay, so that's pretty good. Moving right along here, let's talk about reflections, right? So it all has to do with where are you introducing the negative to the problem, right? So are you introducing the negative out front onto the output, or are you introducing it inside to the input, right? So where are you introducing that negative? So you can see there in that first case, I'm introducing it to the output, in which case you might find that your graph is going to do a reflection over the x-axis. Okay, so you might call that a horizontal reflection, okay? If you go inside to the input and you put a negative in front of the input like that, you're going to be doing a reflection over the y-axis instead, okay? And again, you guys should have learned these in previous algebra courses, so we're just kind of blaze through these here. Next, let's talk about vertical scaling. So this is stretching or compressing, right? So that all has to do with number a being multiplied out front times your output. Okay, now it depends on what that value of a actually is. So what it says here is they start to kind of describe that value by using an absolute value here. So basically they say if a's absolute value, if you were to take the absolute value of it, so make the number positive, if that number is some number that lives in between 0 and 1, so a number that might look like is maybe say like a fraction that lives in between 0 and 1, or maybe simply like a decimal that lives in between 0 and 1, like we're talking 1/2, 2/3, 3/4, etc., something like that, then what that's going to correspond to for us is a scaling effect that goes inward. like compresses inward to each other. So I know that in other math classes you might have called this a vertical shrink, but I'm not a really big fan of that because shrink kind of implies that you're compressing in all directions. But here this is just in the vertical direction, so I like that analogy of kind of compressing like a piston or something like that. That might take a graph that might maybe say in the quadratic sense, the parent function might look like that. If I compress that inward, then it might look a little bit wider to us here. Right? So that's what I mean by a vertical compression in that way, okay? Instead, if we go ahead and see that number that we're multiplying times our output, if the absolute value of that is something that's greater than 1, again, that could be a number like 2 or 3 or 4 or etc., right? Any number that's greater than 1, then what we would get is a vertical stretch, where we are instead taking our function vertically and stretching it. So if the parent function maybe, say, looks like this, if we were to stretch that vertically, then we might get a skinnier looking graph if you kind of picture like stretching that on like a rubber piece of paper or something like that, right? So we would go ahead and stick with calling that a vertical stretch in that case. And again, the math language or vernacular here goes by a factor of a, but again, that's just like a short aside here. So in order to make the next examples a little bit quicker, it does say graph the following. You'll notice that I did already create the graphs for this next one. What I want to do really quickly in this first example is just kind of talk about what kind of transformations would take place from your parent function, which you'll notice that I made a note of down here. The parent function here is simply we're going to have a bunch of variations on our quadratic parent, okay? And so just kind of taking a look, right? So here in the orange example here, we took our parent, which was y is equal to x squared, and then we introduced this minus 4 out back, right? We didn't go inside to x, the input, in minus the 4. We went ahead and squared it first, and that's our output, and now we're going to subtract the 4. So that is subtracting a number from our output, and of course that's going to move us in the output direction, which is going to be down, right? So in the vertical sense, if you minus 4, that's going to be down 4, all right? Moving on to the next one. We notice that we have gone inside to the input and added a 3. That's what these parentheses are doing there. They're saying that before you take that x and square it, we're going to add the 3 first. So that's us going inside to the x input, and we're adding 3. And don't forget that this is kind of like the backwards interpretation. This would be one where we interpret that as going to the left 3 units with our parent function. Okay, and then in that final case where we see a couple of different things going on, I notice that there is a negative out front of the output. I notice that there is a minus 1 inside on the input, and then there is a plus 2 outside on the output. Well, first of all, that negative on the output, that is going to go ahead and perform a reflection over the x-axis, we said. So we'll make a note of that. So we are going to reflect over the x-axis. All right, and then after that, that minus 1 inside to the input, that's going to move us to the right 1. Again, because of that backwards interpretation whenever you go ahead and do something to the input. And then finally, outside on the output, that plus 2, that's going to go ahead and move us up 2. Okay, now all these different transformations, again, just to save time in the video, you'll notice that I've gone ahead and accounted for all of those. I kept my coloring convention the same. My parent function is just plotted there in black, and you'll notice that every single one of these colors here is represented on that graph and with the appropriate transformation. So maybe you want to go ahead and pause the screen and kind of ask yourself if each one of those is the case. But I definitely think that you're going to find that that's going to be the correct answer. Okay. Now, what I want to do is kind of do the backwards thing here in this next example. So we have a couple of square root functions here. You'll notice that I've given these some colors as well. I've already gone through and described the transformations, and now I actually want to go through and draw them, right? So my original parent function is drawn there in black, and let's go ahead and start off with my pink one here, where if I have a minus 1 inside to the input, I interpret that as going to the right 1. Well, all of these different points here, right? I've got 0, 0, I've got 1, 1, I've got 4, 2. I'm going to move all of those points to the right 1 unit, okay? And so that, of course, is going to look like the following here. And I'm just going to go ahead and draw the rest of that graph, okay? So all those points shifted to the right 1 unit, or 1 grid square, and we're going to go ahead and see that the entire curve follows that same pattern, right? Now, on the next one, in the blue case, I have a reflection over the x-axis because I have an extra negative sign in front of the square root on the output. And so what that means is that I'm going to take all of my points plotted here in black on my parent function. I'm going to reflect them across the x-axis here. So this point right here, I notice that that is 2 units or 2 grid squares away from the x-axis. So I'm going to count down the same number of units, 1, 2. I'm going to plot that point. Again, that is us reflecting that over the x-axis. Same thing with the next point over. I have the point 1, 1 right here. I notice that that's 1 grid square away from the x-axis. So if I count 1 down, I'm going to plot that point, again, reflecting over the x-axis in that way. And because 0, 0 actually lives on top of the x-axis, we're going to go ahead and keep that still. That is going to stay put. And we notice that I have a nice skeleton of points now that I can go ahead and plot. and draw the rest of the curve in that way. So if you take that black portion and reflect that across the x-axis, you're going to get that blue portion there, and that would be a quick way to go ahead and sketch that by hand. Something interesting that you'll notice here happens in our green example. So we have a negative both on our output and also inside on our input. So that is going to mean that two different reflections are going to take place. It does not matter which one you take care of first. You just need to go ahead and take care of one. So let's go ahead and do that, right? I might go ahead and reflect over the y-axis first here. And again, remember from geometry class that we just want to go ahead and maintain the same number of grid squares on either side of the line that we're reflecting over, right? So if this point right here on my parent is 1, 2, 3, 4 grid squares away, then I'm going to count 1, 2, 3, 4 grid squares away on the other side of the line, and I'm going to, of course, go ahead and plot that point here. Okay, very straightforward. This next point here is 1 grid square away from the y-axis, so if I go ahead and count 1 over in the other direction, I'm going to go ahead and plot that. And then, of course, the 0, 0 point, that is going to stay put because I can't reflect that over the y-axis if it is already on top of the y-axis. So that's us reflecting over the y. Next, we need to reflect over the x-axis, and that's going to be handled the exact same way as what we did in blue. We're just going to count the same number of grid squares vertically, and we might get a little bit of a picture that looks like this. So you notice that I kind of took care of that in 2 different steps there. Something that I think is very easy to perform if you think about it as 1 step at a time like that. Okay, and we're just going to go ahead and take care of that orange example there last. So it says we need to just take our black parent function here. We need to go ahead and shift it 1 unit to the left and then down 3. So this is probably going to be the easiest one because each one of these points here, I'm just going to go ahead and do that counting, right? So shift 1 to the left and down 3, and you might notice that I've got this little skeleton of points going on right here, in which case I'll just go ahead and create the rest of the graph in that way, okay? So again, that's why we call this a parent function, because we started off with that shape in every single case here, and we just altered the function formula a little bit, and it created all these different colors of children functions that we can go ahead and plot, okay? So go ahead and give the assignment a shot. If you guys have any questions whatsoever, as always, feel free to ask away. I'll be in the chat, but that's all I have for this video. Thank you very much for your attention, and I'll speak to you in the next one.